So we are going to start for the session 1 in room 2 now. And the session is on damage prognosis, which will be chaired by Professor Rukyang Yan. So I request all of you to take your seat in respective tables, keeping one chair at least vacant so that someone can join there and spread across. So soon we will be starting the presentation, like in 5 minutes time. So I'll be announcing all the things shortly as soon as others are there. In the meantime, I'm posting the links for other sessions as well as the workshop. Feel free to move around of the session of your choice if you want, and come back again, which is of your interest. Okay, I can see Rukyang has joined us. Good morning, Rukyang.
Hello.
Hello, Rukyang. Can you hear me?
Yes.
Okay, great. So I'm Arijit. I'll be helping you for this session as host.
Let me turn on my webcam.
Yeah, sure.
Okay.
Hi. So we have, I think, almost all the speakers. Let me just quickly check whether we have everyone. So I think we have everyone here. So as per the schedule, we have at 10:45 by Kanmalung, and then 11:05 by Farhan, 11:25 by Hamza, 11:25. 11:45 will be presented by Hamid, and again I think 12:05 will be presented by Hamza.
Okay.
So we'll be just doing a quick check on others if they are there. I think everyone is here. All the speakers are here for this session.
Okay, then I think we can start, right?
Yes. So whenever we are starting the presentation, only the speaker should remain his camera and mic on. I request everyone else to put off their camera and mic off so that we can hear them properly. There will be 4 arrows at each tile at the corner, right and top. If you click that one, this will expand the view on the full screen. So Rukyang will announce the speaker name, and then he will be asked to come on stage. He'll be presenting the things, and then the question answers, everything we can post in Q&A session, which is on the chat box, which you can find at the right-hand side. Anything in general chat, if you can want to post, you can post on the chat. Okay?
Okay. So I think good morning, everyone. But here, for me, it's already 6:45 p.m. So Welcome to join our session for damage prognosis. So I'm Ru Changyan from Xi'an Jiaotong University, China. So welcome all of you to present your work on our session 2. I think now let's start. The first paper is about influence of temperature on verticrack growth and structural dynamics. I think this paper will be presented by Ken May, right?
Yeah. Can you hear?
Okay. So
Can you hear me?
you can go ahead.
Can you hear my microphone?
Yes, I can hear you.
Can I do my presentation now?
Yeah.
Okay.
You can start.
Can you see my screen? Hello? Hello? Can you see
Hi,
my
we can
screen?
see. Yes.
Okay, good. So, good morning, everyone. If you are in the UK, or good evening if you are not in the UK. It's good to see you all here. And today, the presentation of my presentation is all about influence of temperatures on fatigue crack growth and structural dynamics. So this is a review presented by me and with co-author with Muhammad Ali Khan. So in these presentations, I'm going to talk about the basic of crack propagation principles, and I will also mention about the crack fracture surface from which is seen from the scanning electron microscope. And I will also talk about the basic or the crack propagation analysis. And I will cover up with the effect of temperatures on fractures, initiation toughness, and strain, stress-strain curve at different temperatures. And at the last, I will also talk about how these temperatures have been affected in deformations of the structures. So fractures and crack initiation is very common in mechanical structures or any components heavy duty machines. So we're familiar with this crack. The crack can be of any type, which can be multiple crack or single crack. And crack usually happens to be seen on where there is a stress concentration or any joint part or where it have some material defects on it. So why this crack have been, why there is a crack on this all these surfaces? The main reason or the one of the philosophical reason is that the crack growth is happened because of the fluctuating load. We apply load, we apply differential load. Because of that, it happens, the development of crack origin started. So this fatigue crack life is dependent on cycle history of the loading's magnitude, the residual stresses, the properties of the materials, manufacturing defect, design geometry, and environmental condition. But according to the research, the complexity of crack growth evaluations arises due to random or variable loads applied. Because when we apply a variable or random load, there is a loading interaction effects occurs. Because of that, the evaluation for the crack growth is difficult or complex. But now the question is, how much effect by the temperatures in crack growth? The questions remain unanswered. And so today I review about how people are doing this crack growth analysis based on temperatures. So in this research, I just want to start beginning with the basic principles of crack growth models. According to research, the crack growth models, there are three regions which we can identify in crack. The first one is the region 1. The region 1, we call it the crack initiation region. In these regions, they are largely influenced by microstructures, main stress, and environmental conditions. But in the region 2, we see that the region 2 is the region where there is a crack, but it with steady and linear crack growth. So according to the research, this crack region 2 is linear and steady, and it has a little influence by the microstructures, stresses, or the environmental thickness of the materials. But in region 3, the crack growth is abnormal. It's a core in region 3. Why? The reason is that in this, when the crack reaches to region 3, there is a plasticity development in the materials. Because of this, it has a rapid growth, crack growth, and leading to the failure. So according to the research, it says that in these three regions, which model is suitable to apply for crack growth analysis? According to research, say Paris and Walker law is based or good for analyzing the region 2. However, region 3 and region 1 are underestimated by using the Paris and Walker law. So Walker models have been modified. Paris and Walker have been modified by Foreman. Foreman tried to evaluate their including region 3 by introducing material fracture toughness. So Foreman tried to introduce that part, and then now Foreman can evaluate the crack growth in region 2 and region 3. How about the region 1? It's still untouched. So because of that, the Nagro's model was proposed to represent or to evaluate the region 1, 2, 3. But however, it can be able to evaluate, but with the introduction of multiple parameters, with including crack functions. So now all these three regions have been seen practically, and then I want to show it through how people evaluate through the scanning electron microscope. So this is the pictures of the crack specimen. So here, the first region, pre-crack regions, is the region where it is the crack initiation part. But zone A and zone B, zone A is the short crack, and then zone B is the long crack region. So in this region, zone 1 and zone B are the regions that have determined by intermediate. In zone 3, zone C, this is determined by region 3, which is, we call it abnormal crack growth or failure stage. So now, how people try to evaluate this crack propagation analysis is that some are trying to modify the basic models, and some others try to model it through FEA. And in this research, they say that they can predict the crack size using a surrogate model built from FEA, and then utilizing the material properties of equivalent initial flow size of the crack size. So this is how they do. And then they say that these models can be able to predict the crack size, but it does not account the errors and sources of uncertainty. And this model is deterministic. However, this research also mentioned that there are many sources of uncertainty. So those uncertainty are the loadings, initial flow size, data uncertainty, and model uncertainty, like crack growth law, correct calculation of stress intensity factors, and all this have an individual impact or effect on crack growth prediction. So now, all this crack propagation analysis of crack growth law have been exit, but how about considering the temperature? Because temperature has an impact on the material properties, and the material properties, especially when you consider the toughness of the material. So now I just want to include about the effect of temperature on fracture toughness. On this paper, it say that they try to evaluate how much effect have been impacted by the temperature in initiation toughness. So in this graph, it says that when the temperature increases, this initial fracture initiation toughness increases. And this is more equivalent for dynamic loading than quasi-static. However, in this research, it's also mentioned that this fracture initiation toughness is noticed to be of strain rate sensitivity. So strain rate sensitivity. So to do that, some other people also doing the research on stress strain curve at different temperatures to see how it varies with different temperature. On this graph, temperature of 800 degrees Celsius, we see that no stress value of this much, and then the strain value is increasing. But if we decrease the temperatures, we see that the stress value increases and the strain life decreases. And it's the trend is showing like this. If you increase the temperature, you will see the more strain and less stress develop. But if you decrease the temperature, you will see that more stresses and less strain. So from this experiment or from this research, it means that the temperatures have a very much influence on fracture toughness. So going on, moving forward, I just want to mention that the temperatures have also impact on deformations of the microstructures. On this research, they conducted a research on polymer beams. So the instability of temperatures, the instability of the mattress occurs for different heating temperatures, and then they consider that when you consider about the temperature, you should also consider about the thermal properties, which we normally included like heat conductions and non-heat conduction. This experiment conducted with heat conduction and non-heat conduction. When the red line indicates about heat conductions, and then without heat conduction was there in for with blue lines indicates the without heat conduction. Yeah. So red line indicates about heat conduction. So when they compare the two, you will see that when you include the heat conduction, you will see that the instability occur at greater time. But when you consider about non-heat conduction, you will see that it requires less time. So the temperatures also have an impact on the deformation. So moving forward, I will show you the trend. So it's remain the same for different frequency zones. Now, when you say that the response of the beam under different temperatures, some other people also doing a research because temperatures have impact on thermal properties. That is why this research has been done to see how much impact has been done from temperatures in thermal properties. That's why this research is done to show that when you increase the temperatures, young modulus or elastic modulus decreases. But if you increase the temperatures, you will see that thermal expansion increases, which is related to strain. So this means that when you increase or decrease the temperature, the material property change, and it is indirectly affecting the crack initiation. So in this graph, it says that if you consider the heat conduction and without heat conduction thermal effect, it shows a result that the deformations keep on changing. So this is how the importance of temperatures have been need to be considered for crack evaluation. Here, according to them, it said that when you consider about the temperature, the stress intensity factors keep moving high or it's keep more value. But without heat temperature, without heat conduction, you will see the value is low. So that when you have temperatures, when you have applying the different temperatures, you will get a different value for all the stress intensity factor, which is the functions of crack growth. So that is why people try to introduce temperatures along with the crack propagations instead of utilizing only the normal basic fundamentals models. So in this review, I just want to conclude with that when you evaluate the crack growth propagations, you also need to consider the impact or the effect of temperature, because when you apply temperature, it changes the matter properties, and the changing the matter properties also impacted the uh, crack growth rate. Because of that, yeah, if you want to modify or if you want to have a proper or accurate crack growth evaluation, you need to consider this temperature as a must. So let me put a conclusions with this question. Can we prevent crack propagations and fractures during service time? Well, this is because of this that we are doing the experiment. We are doing research on it to answer this question, and we try to prevent it. We try to minimize it. We try to optimize the crack propagation. Well, the next question, can we ignore the effect of temperatures on fatigue crack growth propagation and structural dynamics? I think so. We should not be ignorant about the temperatures if you are more or if you want to see the accurate results of it. And so today in my presentation, I just want to conclude that the effect of temperatures have a very much importance in parameters to be considered whether you are analyzing the crack propagation or structural responses under different temperatures or with dynamic loading. So this is my presentation. Thank you very much for attention.
Any questions from the audience? So I have one question. As you show, there are 3 different stages for the crack propagation.
Yeah.
So normally when we do the prediction, if we do prediction, so can we get the changing point for different stage change? Is there any way we can know, oh, okay, when it will turn to the second stage, for turn into the region 2?
Mm-hmm. I don't get it. What is your question?
My question is, if there is any way, then we can determine this crack propagation change from region 1 to region 2.
According to what I have read from the papers is that there is no proper way to evaluate this region is the crack region 1 and this region is the crack region 2 and this is the crack region 3. We cannot able to differentiate, but according to the research with the microscope scanning electron microscope observations, it showed that there is a pattern of region 1, region 2, region 3.
Okay. Yeah, because in different region, if you need to do prediction, you need to use different equations, right?
Yes, but according to the research papers, it said that NASCRO's model can able to predict, it can be able to capture all these 3 regions, starting region 1, region 2, and region 3. But if you are using the Paris law, it will be only concentrated on region 2 only, and then you are underestimated region 3 and region 1.
Okay, okay. Thank you.
You're welcome.
So, if there's no question, I think thank you again. So let's move on to the second paper. The second paper is about coupling geometric and microstructure gradients in fatigue crack formulation. I think this paper will be presented by Farhan Ashraf.
Yeah. Hello. Good day, everyone. Can you hear me?
Yes?
Thank you very much. Okay. All right. Hi, everyone. Have a good day. Do you know that when we have multiple gradients that facilitate the crack to grow in the metallic structure, so it's make the fatigue prognosis computationally challenging. Here today, I'm gonna show the coupling of different gradients in fatigue crack formation. My name is Farhan Ashraf. I'm currently a PhD student at Through Life Engineering Services, Cranfield University, and working on fatigue damage prognosis. So let me introduce you to the problem. A micron size scratches that have been found on an aircraft structures as a result of aircraft maintenance. They act as the micron size notches and have a potential to nucleate and propagate the crack under the cyclic loading. So the cracks are comparable to the grain size and driven by the local shear. Since the amount of the local shear is controlled by the local microstructure, so thereby these cracks are also sensitive to the microstructure and normally termed as the microstructure sensitive small fatigue cracks. So here in this fatigue problem, so there are actually the two gradients. So one is the geometric gradient that is coming from the scratch, and the other is a microstructural the gradient. And for the fatigue prognosis, we need to count both of this gradient. The coupling of this geometric and microstructural gradient through the conventional crystalloplasticity model is an expensive way of modeling, and it requires the high level of computational resources. Alternatively, we have proposed to quantify each of these gradients separately and couple them independently, and they serve as an economical model, and it is less computationally intensive. So here I'm going to explain the coupling of geometric and microstructure gradient through the expensive and economical model and make a comparison. So first of all, since I have mentioned the small fatigue cracks, they are driven by the local shear. So we have considered here a fatigue indicator parameter based on the shear range proposed by the Fatmi-Soshi. It's actually served as the subrogate driving force in the modeling and can be used to study the effect of different geometric and microstructure gradient. So following on, these are the driving force in our modeling. So first of all, we study the explicit effect of microstructure on the driving force, that is Phipps. So for this one, we have created a finite element model with roughly 50 grains to study the effect of microstructure on Phipps. The literature showed that this microstructure sensitive small fatigue cracks, they initiate and propagates along the slip bands. The following on, we have created the artificial slip bands in each of the grains along the crystallographic direction. And we're gonna, in this study, we're gonna investigate that the crack initiation and propagation along the slip bands. So the next step is to find the hotspot where the crack initiates. For this one, we have implemented the crystalloplasticity model in the abacus, and we evolve the model until the stress strain curve is stabilized. And at that step, we quantify the FIP in each of the slip bands, and we average over the slip band domains. The next step is to find which band among all the bands that have the maximum value of average FIP. And this is what we termed as the minimum life band. So only the one band is referred to as the maximum value of the average BIP, and it's a minimum life band. And this is considered to be where the crack initiates. Now, the next step is to extend the crack along that band. So in this figure here, so we have this minimum life band, and in this plot down below, on the y-axis, we have the average FIP normalized by the average FIP at 0% crack extension. That's how it is 1. And on the x-axis, we have the distance along minimum life band. We extend the crack by deleting a certain amount of element of that band, that is roughly 9%. And this deleted element is shown by the blue color in this figure. And these elements are not available more in the simulation, so they are termed as a deleted element. So we delete this element and we average the FIP in the remaining elements, and that is shown by this blue dot in the plot. Following on, and this is done by after every 2 loading step after the stabilized cycle. So we keep on deleting the 9% incremental element and averaging the element over the remaining element of the band and calculating the effect of driving force, and just keep on deleting the element until the full band is cracked. This is the way we extend the crack in the minimum life band, and we study how the driving force is changing as the crack is extending in the minimum life band. And this shows that the driving force has a decaying trend as the crack extends in the grain, and which is similar to the literature findings. So this result corresponds to the one set of realization, one set of microstructure. We repeated the same set of simulation with a different microstructure, and interestingly, we found that this decaying behavior of driving force as the crack extends is consistent. So this is normally termed as the microstructural gradient. Moving on, now we add in the geometric gradient with the microstructure gradient, and we termed as the expansive model. So we done the similar set of simulation I have explained in the previous slide, the same crystal plasticity simulation. Now we add in the geometric gradient with the microstructure gradient. And we adopted the same procedure as explained in the previous slide. So we deleted the little by little element in the minimum life band, and we plotted the gradient of driving force as the crack extend along minimum life band. And here we found that the gradient is much steeper actually. So this is basically expected because we have a notch here that was not present in the previous case where it's just the explicit microstructure. Now this really gives us a notion that can we really quantify this geometric gradient independently? So we propose an independent estimation of geometric gradient through the economical model, and we created a finite element homogenized model without any microstructure, so having only the notch. And we propose to capture the gradient of the notch by estimating the local shear, the maximum value of the shear strain along the radius. On this plot on the left side, we have the maximum value of the shear strain normalized by the maximum value of shear strain at the notch tip. And on the x-axis, we have the distance along the radius away from the notch. And we have calculated this maximum shear gradient at different angle along the notch. And interestingly, apparently, it gave us the same decaying trend as we have seen in the previous crystallograph simulation. So this is just the independent geometric gradient. Now following on, we propose the independent coupling by, we have the independent geometric gradient I have shown in the previous slide. So we independent couple it with the explicit microstructure gradient to reconstruct the independent coupled effect of both gradients. And then this is done by the economical model that is less computationally intensive. Now we compare this result with the expensive crystal plasticity simulation, and we found that this is roughly the same with some level of uncertainty. So thereby this is in a good agreement. So following on, we conclude that the expensive model that agrees well with the economical model, and that gives us the advantage of calculating the independent geometric gradient coupled with the microstructure gradient to for example, to come up with the coupled effect of both the gradients. And this, as we broaden the scope of this approach, so this gives us the advantage that, so for example, in this case, we have a notch as a geometric gradient, but in the real fatigue problem, we have several other geometric gradients, like we may have a circular hole or may have other things. For that case, what we need to do, we independently quantify the effect of that geometric gradient. Since the microstructure gradient is not changing, so we can couple that independent gradient effect and we can make a fatigue prognosis with the less computational intensive simulation. Thank you very much. Thanks a lot. If you have any question, please.
Questions can be posted in the Q&A section in the chat box.
Yeah, Gustavo asked, how do you extend this to live quantification?
Okay. So this is only the driving force, the effect of the gradient. So we need to couple it with the, for example, with the equation, the life equation. So for example, in the life equation, we have the driving force as a function of crack length, and that's having the direct relation with the life. So we can directly use this couple gradient over there, and we can propose the life actually.
Okay. Any further question from the audience? Okay, if no question, we thank you, Farhan, again.
Thank you. Thank you very much.
Yeah. Then we go to our next paper is about wear behavior of 3D printed PLS surfaces for super hydrophobic interaction. This paper will be presented by Hamza Shams. Okay. Yeah. Hamza, you can start. Can you hear me? Hello, Hamza.
Give me a second.
Okay. Yeah. You can start.
Can you all hear me?
Yes.
Okay.
You can, yeah, you can start.
Okay. Good morning, everyone. So the work I'm presenting today is regarding where PLA surfaces for super hydrophobic interaction. A little introduction about me. I'm the Shams. I'm a visiting research student in manufacturing at SATA. My supervisor's name is Dr. Muhammad Ali Khan. I'm basically a student from NUS, Pakistan, and I'm here attending Cranfield as a visiting student just for my PhD research. So with regard to this presentation, these are the authors that contributed towards this work, and their affiliation are as listed on the presentation itself. So I'm the first author, and my supervisor's name is also over there. The rest of the authors are from NUS, Pakistan. A formal thank you to all these participants for supporting this work. So this work is primarily funded by Commonwealth scholarships. It was jointly supported by Through Life Engineering Services and NUS. And Mr. Murray, he's a resident at Cranfield Village, and he actually supported us with the 3D printing facilities while we were having the COVID-19 lockdown period. So this work was not possible without his support. Beginning formally with the topic itself, We are looking at an experimental study of wave behavior of 3D printed PLA surfaces, super hydrophobic interaction. This is just for a journal audience information that we wanted to dissect the topic for everyone's understanding. That we're going to study the damage caused by mechanical erosion on a polyelectric surface, which is super hydrophobic or hydrophobic in nature, that it is scared of water. So before going on to the actual work, I wanted to introduce the topic for everyone's information. So the motivation behind this work was primarily that WaterAid and UNICEF has listed Pakistan as the 7th country that has inadequate basic sanitation facilities. We'll have like 42% of the population still remains without access to basic sanitation. So this was the primary motivation for me to pursue my PhD. So I really wanted this to be known as. Choosing Cranfield was also one of the reasons, because Cranfield recently completed a project funded by Bill and Melinda Gates Foundation, which was on water-free sanitation, the basic toilet. So that was conducted by C4D in Cranfield University. So recent developments in the world has opened gateways to revolutionize the basic sanitation. And on learning more about the hydrophobic surface modification, several important applications can be considered. They are as flashed before you. So we can look at solar panels, waterproof electronics, sanitation, anti-corrosion materials, transportation in anti-icing, and low-pressure transportation in pipes. I hope I'm clear to everyone. Hello. I guess. Am I clear to everyone?
Cannot move on.
Is my voice clear to everyone?
Yes, your voice is clear. Probably you can maximize your presentation so that we can see.
It's maximized on my end.
Okay.
Weird. Let's see. Is this maximized for you guys now?
No, it's not in slideshow mode. You have to go to in presentation mode.
Yes, just give me a second. I guess this is. I need to do this now. And I'll do this now. Yeah, is this now clear to everyone?
Yes, thank you.
Sorry. Yeah, okay. So we're defining hydrophobicity as the first thing. The literal meaning of the word is scared of water. It's an application of biomimetics. We'll come to biomimetics in a while. How do we define hydrophobicity? It's when your contact angles, that is the liquid that is making the angle with the solid surface, as seen on the right, is greater than 90 degrees or equal to it. And the measurement of contact angle basically gives you the measurement of wettability that a liquid is making with the solid surface. So you see 4 wetting states on your right. One is a non-wetting behavior where the contact angle is almost 180 degrees. When the contact angle is greater than 90 degrees, we call it as high. Okay, it's actually written in a wrong way. So this is low wetting and that is high wetting. Vice versa. And the perfect wetting is when the contact angle is at 0 degrees. So moving on, you can model hydrophobicity by the Young's contact equation. It's a well-known equation that was developed in 1805. There are subsequent equations that were developed onto it, which are known as Wenzel and Cassie Backstrom model, which we'll can discuss in the next few slides. So the equation states that the cosine of the water contact angle is basically a difference of the surface tension between solid minus solid liquid interface divided by liquid vapor interface. So this is basically the contact angle calculation in this particular site is calculated using the Young's contact model. So as we discussed, this is an application of biomimetics. This behavior is widely seen in nature, where buckskin, blue morphoradius, butterfly wings, and lotus leaf exhibit this behavior to their fullest. Here we also see another example that we conducted ourselves. This is basically a small experiment on a super hydrophobic coating that we received from Ultra Ever Dry back in Pakistan. So as you can see, water does not stick to the surface at all and just keeps on flowing. So if you can maximize this to a very certain level, you will also see the water droplets actually bouncing off the surface which is also known as the bouncing drop test, commonly conducted for these surfaces. So the wetting states, the two wetting states that we are discussing here are today is Wenzel and Cassie Backstrom. With regard to the Wenzel state, it's when the water droplet is fully in contact with the substrate surface down below. As you can see, so the water droplet basically makes a full intimate contact with the surface, and in doing so, when you add more water to it or the droplet size is increased, so basically the adherence is so strong that water droplet just grows and does not leave the substrate it was touching before, so you receive high contact angles that way. In the next, which is the Cassie Backstrom model, it's when the droplet is actually not in intimate contact with the bottom of the surface, but only on the top, and the rest of the bottom is basically filled with a fluid or in air in this particular case. So you actually receive very small tilt angles. Well, a tilt angle is basically when you move the surface to a certain angle, say less than 5 degrees or 10 degrees, the droplet will just slip off. So that is when you have the Cassie Backstrom. So how is hydrophobicity characterized? You basically can use any of these methods. The most common ones are static contact angle measurement and the tilt angle measurement. But yes, other methods are also commonly used in papers widely. We're going to discuss the static contact angle measurement model in a while because that is the one we followed. We also deducted, but the results are listed in the paper and not discussed in this particular presentation for that matter. So how can hydrophobicity be created on a surface? You basically need to just modify the surface property by either coating it or you can texture it as shown in the figures. So if you coat it, you're going to end up with a pattern as seen on A. And if you start texturing, you will have a more ordered structure. You can also have an unordered structure, like a fiber structure in which you're going to have a lot of air pockets well dispersed in the substrate layer, which is going to again support this behavior. So you can have regular and irregular surface texturing, and that can be achieved with slight chemical modification as well as mechanical means to obtain low surface energy, so that your droplet actually rests on the surface and does not fully immerse into it. So at the end of the day, it all comes down to the point what you want to create. If you want to create regular patterns like recessions, pillars, spherical top structure, you go for a more ordered technique. And if you want to create fibrous structures or irregular patterns, you go for like chemical etching and stuff like that. So these are some of the techniques that you can use. Our interest was to use 3D printing techniques primarily. We use a low-cost fuse deposition modeling technique in this particular experiment. So I'm going to discuss the basics of that in a while. Obviously, when you talk about 3D printing, if you look at the resolution of these parts, these are very, very small parts, like 500 nanometer is given in this particular semi-image that you see at the bottom where you see cylinders. So when you talk about 3D printing, if you can only use higher resolution 3D printing like photon polymerization and stereolithography to obtain such a small structure. When you talk about low cost FDM techniques, it's not possible to achieve such a small structure for that matter. So how do we go past that is we actually study this layer by layer deposition effect, which is also known as the ladder effect in literature. So this distinctive geometrical feature, which is known as the ladder effect, can actually support air to be filled like this. So you have multiple layer by layer deposition, as you can see over here. This is your extruder, which is going to be depositing the extruded layer. So once you have this, you're going to end up with a layer by layer deposition structure as shown over here. And if you stack multiple of them together, you're going to end up with a porosity over here, where you can stack air or some other fluid in which you can easily generate your super hydrophobic behavior as shown here. In this particular experiment, we are modifying H and we are trying to study its effect. And our interest is not on the entire deposition structure, but only on the semicircular edges that you see over here. So basically, by modifying the layer height, we are changing the behavior that can be seen in these semicircular edges on your left and over here. This is the actual air entrapment side. The rest of the material just for structural strength. I'm not going to discuss much on that. So this effect results in natural profiles that can be exploited as multi-reentrant edges common to hydrophobic surfaces. And these multiple reentrant edges can also be or host micro and nanoparticles as shown over here. So if you use a tip coating or spray coating application, you can also stack more particles like nanoparticles over here to create further reentrant edges on these sides, like shown here. So in this way, you're going to end up with multiple profiles that can support any kind of liquid on top of the surface. So for this particular experimental investigation, we wanted to test the wear resistance of the multi-reentrant edge profiles. We wanted to validate changes in wetting skin by determining changes in water contact angle. And we wanted to identify optimal layer height, which results in maximum wear resistance and maximum water contact angle. So steps we followed for this one was, our choice of using a disk specimen was because we are actually investigating tribological wear. So we wanted to take a disk specimen because the particular equipment only uses disks for investigation. So at the end of the day, we wanted to use a disk specimen. And obviously, I mentioned that our interest is to investigate these semicircular edges. So instead of printing it flat, we printed it vertically so that these edges are all translated onto the side of the specimen itself. So we chose 4 layer heights: 150, 250, 350, and 450. And we used 0.4 mm nozzles for these particular layer heights and 0.6 mm nozzle for these particular layer heights. The choice of nozzle was set because if you look at the flow map behind the 3D printing, you cannot actually print a 450 micron or 350 micron surface using a 0.4 mm nozzle, because at the end of the day, the layers will not stick to each other. So you can only use an 80% a layer height that is 80% of the nozzle diameter itself. So for this, we had to change the nozzle. This also gave us some good results afterwards. So we're going to discuss that right now. And contact angle measurement, as shown over here, was conducted with 10 microliters of double distilled water using oscilla contact angle meter. This is the tribological experiment that we conducted. We used this specimen that were burn out using TRT ball figure. So this is how the ball was oriented against the reentrant edge profiles. The sample was revolving this way, and the ball holder is basically applying a 10-20 newtons load. The ball we're using is ceramics, which is common for tribology of plastic specimens, and this is how the specimen was after the investigation. You see 2 wear scars over here. They are for different investigations. For repetition, we actually conducted on both the outside and the inside edge. So you see 2 scars over here, but this is how the wear scar looks like. You see wear scars. You see some foam region as well because of heat generated during the wear process, and you see some erosion marks as well because the material chipped off from this particular region. So coming on to the results, the penetration depth is found to be up to 225 microns in 150 microns layer height, whereas only 1000 microns in 450 microns as shown over here. With regard to coefficient of friction, it is also found to progress rapidly to 1.2 and 150 micron, which is this blue line, while it is only 450 micron layer height as shown over here. So before till 500 seconds, the 450 micron layer height is quite sturdy, but after 500 seconds, we see this sharp trend. So basically, the top layer was more or less eroded, and now the bottom surface started interacting with the ball. So that is why you see this particular trend over here. And this particular change can also be attributed to more material deposition and thicker layer when printed with 0.6 mm nozzle, because obviously when you change their height and you change the diameter of the nozzle itself, you ended up with more material being deposited per layer, which can also be attributed to this trend. But the more interesting effect was this one, because as you change the layer height, you end up with higher contact angles as well, as can be seen over here. So for each layer height, you're getting a better contact angle. This is due to an increase in the peak-to-peak distance, which is layer height, which limits the water droplet from with its high surface tension to spread out. So if you visualize this particular image that we have shared here, so these are the layers being deposited, and this is the water contact angle. So as you increase the layer height, you end up with more steeper hills over here. So the water behaves more obtuse, or you can see you get a higher water contact angle over here. So in conclusion, we develop multi-edge profiles by layer deposition, and we can say it plays a significant role in altering the wetting state. Our wear indicate that wear resistance increases when the layer height increases because of the change in nozzle. Because if you do it with the same nozzle, you might end up with very similar results. Like if you take layer heights like 150, 200, 250, and 300, you might end up with very little results, very similar result, because as can be seen over here. But once you use the 0.6 mm nozzle, the difference is actually more. You see a 20 degrees difference almost over here, 2 degrees over here. So in future work, this was like the foundation work before we started anything. In future work, which we're currently doing, is basically a plate foundation for modification of wetting state using 3D printed surfaces, and we're basically applying this particular phenomena in generating slips right now, which is slippery liquid infused porous surfaces, where we're using these edges to our benefit and create more porosity inside the substrate itself. So I'll open the floor to questions if you have any. I'm sorry if I was a little fast. Yes, you can see this presentation. I can email this to you as well. And if you have any further questions to discuss afterwards, I'm more than happy to entertain them.
Any questions from the audience? So I just have one curious question. When you print layer by layer, can it be easily controlled? Every for each layer, they can be printed the same.
Yes, we can actually consider than that because at the end of the day, this is being controlled by the diameter of the orifice of the extruder. So if you say you use the extruder, which is like a strange, or even we use brass extruders right now, but say you can move to strange and you can even control this layer height to say less than this, what we're achieving over here, say 5 microns or even less. The same changes is see the same changes in contact angle with layer height for different size water droplets, or all test with the same drop size. Okay, same droplet size. Each investigation. If you're asking, basically, we basically use the same droplet size each investigation. That is the question by Sam. Do you see the same change in contact angle with layer height for different water droplets, or all test with the same water drops? So we're using the same water drop size, and we're taking that as standard, and we're just changing the layer heights. I hope that answers your question.
So is there any further question? Okay, we thank you, Hans, again. So we'll go to our next paper. It's about string self-sensing, tailoring in functionalized carbon nanotube epoxy nanocomposite in response to electrical resistance change measurement. I think this paper will be presented by Hamad, right?
That's correct. That's me.
Okay, so you can start.
Sure. I'm just trying to share my screen. Can you see this now?
Presentation.
Excellent. My name is Hamad Yazdani, and I'm actually presenting on behalf of my PhD student who couldn't make it to present today because we had kind of an emergency to go back to China. So the majority of work has been done with my, of course, my brilliant students, Donglin Ann and Jim Nouri, and I've been actually been a part of our team who actually got support from our other academic colleagues across UK and Cranford University. The majority of work has been done at Enhanced Composite and Structure Centers at Cranford University. Just want to introduce myself. I'm an associate professor now in aerospace structures at the Aerospace and Aeronautic Research Centre at City University of London, but formerly I worked at Cranfield University for about 4 years, where we established this research and still an ongoing research as well. As turned out that I'm also a visiting academic at the centre at Cranfield University. A number of affiliation, but one of the important I wanted to draw your attention to, because we're going to talk a little bit, is I'm an academic member of the Commercial Aircraft Composite Repair Committee, which is hosted by EASA and FAA, the European Aviation Safety Agency and Federal Aviation Agency, shortly called CACRC. So just jump to that because we don't have enough time. That's where I'm actually at the platform that I'm working. There's an urgent need. It's been decades that this message has been sent across to different sectors and communities that there is an urgent need for eco-friendly, sustainable, and smarter transport structures. And why? Because what we are about to experience, I cannot emphasize this more, in different kind of organizations, what we are about to experience hasn't been experienced for about 3 million years. And we have to brace for impact, but we actually need to work on loads of clean energy equipped transport, integrated light structures, impolite connectivity, eco-friendly, cost-effective processes and safety to achieve the zero net emission, that's our net zero emission purpose of all. So many work has been done already, and everything actually is kind of devoted to the underlying mechanism of all of this process getting together. Either you're working in an Industry 4.0 platform or climate change action. The science of integration instrumentation in aerostructure, especially in my area, is super important. Let's jump to the aircraft composites aircraft. We're talking about a very critical high performance structures which has been designed to sustain very high fatigue load and aerodynamic load and varying operating conditions when in service. So it's a very highly conservative sector. And we talk about using of, for example, carbon fiber composites at the volume fraction of more than 60%. Carbon fibers, each 6 microns to 10 microns to 15 microns about diameter in the primary structure of the aircraft. I'm talking about the wing structure and the fuselage structure, where the majority of the load is going to be taken up. That's where actually, if there isn't going to be any damage, there may be a catastrophic failure, and there's quite a very high substantial amount of turnover annually of a repair of this sort of structure. And we know that already there are millions of parts either in aluminium aircraft, so majority of aluminium aircraft, or composite aircraft, and also millions of fasteners, which add to the weight of these structures. And not only weight, they might actually come up with loads of assembly issues in terms of joining composite to metal or composite to composites. Some of these joining are being done by fastener rivets and bolts. So there's loads of research, and I've been actually partially involved in some of this research, that there is essentially a need not only to remove these fasteners as much as possible, also actually to come up with a totally smart design to how to embed these fasteners for joining assemblies. And I just imagine in an aluminium aircraft, either civil or military, they're undergoing loads of failure types, either caused by service flutter load, like these top images, or the bottom left image, or divergences. It can be actually some impact that is caused by the service, the maintenance, repair, and overhaul ground vehicles, for example, on the bottom right damage, or bird strike during landing off or takeoff, and also lightning strike. So it's lots of type of damage is happening. And if you look at the composite structures, made of a multi-millions of structures itself, because we got multi-layers of composite layup all around. I actually intentionally put this because we wanted to say that it's not only in aerospace, it can be in any high-performance structure like automotive, that you may end up with the composite damage across matrix cracking, a polymer matrix. We're talking about a fiber fracture breakage, disbonding or debonding, delamination, and fiber pullout. So loads of research being done there. Just imagine that we don't need to get catastrophic damage caused by flutter, for example, or ground vehicle substantial damage or bird strikes. We can have a slight damage of tip or tapping of the specimens, like this experimentation. You see the video here on the low velocity impact that will cause up to about 100 joule of energy only. So you don't see that much of damage on the surface of the very high performance structure. I mean, that material M21 has been used in A350 already. But if you scan it or you do the X-ray measurement, you see there's a substantial damage inside, needs to be taken care of. And bear that in mind that a majority of this impact energy is dissipated by a very devastating, let's say, sort of damage called interlaminar delamination, based on our research, of course. And there are loads of improvement towards moving towards thermoplastic layup using automatic placement. It doesn't actually eliminate the danger of ending up with interlaminar delamination, which is quite dangerous because, first of all, it's very difficult to see. Unless it's loaded, the structure is loaded, you wouldn't be able to see that. But anyway, there's loads of talk about that. It's just bringing up in the state of the art in terms of making the move towards highly integrated composite assembly, which is super expensive to do and super critical to do, like this brilliant dreamline of B787 fuselage part structure that's being filament widened, and then put the whole thing inside an autoclave the size of probably the warehouse that you have. It's super expensive to make that, very, very difficult to control, but people have to aim for that because they want to end up with integrated structures to avoid such voltage structure damage and avoid any uncertainties associated with the layup, let's say. And that's the scale of the turnover I talked about at repair, that what happens, like a clean room you make as a protective environment to go there and do some polymerization, let's say epoxy polymer bonding. And that's another evidence within the Clean Sky Horizon 2020 funding that we need, for example, longitudinal fastener-less joining technology in an automated, very, very controlled way, or this very interesting evidence from Airbus Space and Defense that they're looking for 3D printing of chopped fabric, ripped composites, thermoplastic inside longitudinal fiber composite, still thermoplastic at the skin of a civil aircraft. So loads of evidence to say that we don't want fasteners, we don't want any additional things, we need really integration. That's the same with the transducer and sensors you're going to embed inside. And we're looking for highly integrated transducers that they don't interfere with the structural integrity, they don't interfere with the with the weight, and they don't interfere with the aerodynamics purpose for providing a very good surface. So one of them, for example, you can say basic piece of transducer. I mean, I'm not only talking about in existing non-destructive inspections, we're talking about the real-time structural health monitoring technologies, right? That you can actually embed the strain aid gauges or piezoelectric sensors. So whatever you're gonna do, you're gonna embed them. Rather than that, it's very, very well mature. I mean, no offense to those researchers that they're working a lot on this, but for aerospace, it's very important that we get rid of them and come up with something that it can self-sense itself, like a smart structure, if you may. It has loads of advantages if we do that. There are loads of advantages with, for example, putting fiber optic sensor inside the structure. I'm not talking about them. I'm talking about advantages of the kind of a new direction of the technology towards smart structures, and that's multifunctional non-composite for real-time sensing. One of the big advantages is that they're going to be a part of the structures. You don't need additional cabling. It's going to be cable-free. It's going to be battery-free, right? You're going to still got some electronic accessories at the end of somewhere, but on the structure itself, it's going to be fully integrated. And when that's damaged, you would be able to repair it via injection of the resin, which is smart already, right? That's sort of no excess weight, repairability, and of course, less complexity, made by the multifunctional non-composite very desirable for industries now to think about how to move. We actually specifically working on using carbon nanotubes to make multifunction non-composite for smart sensing, and relying upon, because these materials are electrically conductive, we rely upon their change in resistivity, let's say, and that's sort of the material we're talking about here. So that's our material synthesized by the chemical vapor deposition. That's when we talk about these hollow structures, which are really, really low weight, and the aspect ratio of the length of them over the diameter of them is about 10,000. This starts from 10,000, it goes up to multi-millions, right? If you make them in a very long shape. So the size of these is about 100 nanometer, right? And we expect that the electron chain reaction is going to start along the long length of this. So we expect sort of an interaction and contact points between this carbon nanotube, as you see on the top left side, making the non-conductive polymer conductive, and then take advantage of not only for toughening, also for strain sensing. That's sort of the technology I'm talking about. We're very pleased to say that after some years of research on making enabling adhesion failure sensing in composite assemblies for aerospace structures, we came up with this not too bad publication, scientific reports, and you would be able to see lots of innovation in there. But the matter that we wanted to report is that we can actually interpret using the very well-known contact point method that you see at the bottom right of the carbon nanotube contact point. When they actually lose the contact or they actually establish new contacts, you would rely upon them, and then you can have an interpretation of adhesion failure, let's say. But we see the challenge in a second. So that's the challenge. Sorry about the noise. Let me just mute it. That's the challenge we're talking about when we do a lot of wiring still. Let me just move on for the time. So yeah, we use lots of facility to validate this, like the laser extensometers and situ real-time measurement. That's where the specimen or the smart specimen has been set up with a two-prop conductivity measurement or resistivity measurement, and that's where I'm talking about. There are still loads of requirement for electronic accessories and algorithms. For example, for our case was written by LabVIEW. Thanks for Isidro and his group to help us. But if that happens, the scale-up is very possible very, very soon and very, very soon in the future. And that's why, because there are continuous nanofiber production like this one in the Graphic Composite Center, that you would be able to make multimeters of carbon nanotubes and then tuft it inside robotically and the structure. And then you would have a very, very reliable sensing technology, let's say, if that hadn't happened. It's just imagine the scale of mitigation of the complexity with the piezoelectric sensors, for example, the schematic shown in the aircraft wings, for example. This is what I took last year when there was no corona, let's say in JEC Composite 2019, and showing a component of aerospace. This is on the top left, instrumented, right? Loads of sensors on it. And you see, for example, a zoom view of that might have an IDE in place as well. It's very difficult still to embed some sensor, but they're very reliable, right? And that's the challenge about how make multifunctional nanocomposite for smart sensing reliable. So the objectives was defined for this project as well. So what kind of process parameters might have an effect on reliability of this smart sensing? And we say that maybe adding a surfactant would be an issue, and it is actually an issue, because we came up with mixing the carbon nanotube, ultrasonification of inside a surfactant, and then mixing it with polymer, because we wanted to anyway come up with a straightforward or in conventional saying an easy process to make a smart composite rather than a very complex process, but it's still applicable to scale up. Of course, a chemical vapor deposition was used using ferrocene and toluene to make our carbon nanotube on quartz plates, good quality, averagely. So I just want to skip this and I say that yes, we came up with different samples at different dispersion densities of carbon nanotube and surfactants. You would be able to access all of this information on the paper, which is online already if you're interested. And there are surfactants levels that we have actually changed to see what are the effects, like a comparative study. We did, of course, the two-prop conductivity measurements, and we did the real-time strain measurement of these, cyclic loading and quasi-static loading only. At different, let's say, points or critical points of the specimen with it. That's just to give you an idea. The specimen, the gauge length of the specimen from 0.1 to 0.4 is about 14 millimeter. And as you just saw, the some other information about what instrumentation were available, as well as our LabVIEW program to carry out this real-time measurement. You just looked at the video. I just want to skip this, just a repetition. That's where we came up as one of the main outcomes. And that's actually what you're looking at is the change of electrical resistivity, which is in brown color or orange, if you see that, versus the number of cycles, but we had to put time as well, the number of time in a cyclic loading when you increase incrementally the load level. So we came up with a mimic of varying operating condition in a very controlled laboratory scale. But we ended up with very interesting result. This is in the scientific report paper on the composite assembly adhesion bonding as well. So we did this strategy with cyclically increasingly varying load or something like that. I don't know how to put it. Just imagine that if you focus on the blue line, a dark blue line, so there are loads and the cycles of these loads changing in terms of the strain at the loads. The loads have been incrementally increased, 150, 300, 450, 1,000. And we ended up with having some failures at the end, let's say the ultimate failure in this specimen, where we actually wanted not to have, or being at the verge of the damage occurring inside our composite. But what I can say that if you compare, for example, two curves of the orange one and the blue one, the one that has got the highest difference is the best one, all right? But because we want, at a very small variation of strains, we want kind of a very high sensitivity of our smartness, meaning that the resistivity, we want that to be highly increasing or decreasing with a very small or tiny amount of strain variation. That's what makes a very good sensor a very good sensor in terms of, and that's been identified with the gauge factor. So you can guess that, for example, the top right image would be the most desirable image of this difference, because the highest difference that we got the resistivity change with the blue line, which is cyclic load. If you draw the this curve normalized by the strain value called gauge factor, so we got a difference in the ratio of difference in resistivity with respect to the strain over the 40 millimeter specimen, for example, you would be able that with the open 5% surfactant or 1% surfactant, we got quite significant difference in the gauge factor sensitivity. So that's where actually we try to identify and report that yes, with there are sensitivity and quite significant, but it is possible with taking control of a straightforward mixing, come up with a good sensor. And actually, good sensors, it's another report in our scientific report journal article. So you would be even achieving a better gauge factor comparable, quite 10 times better sensitivity than strain gauges. Anyway, I wanted to end up. I just wanted to say that look, if we do pure epoxy cyclic testing and epoxy non-composite testing with a carbon nanotube inside that different dispersion and different stuff like that, you won't see that much of difference in terms of mechanical response. So this has been identified here with drawing our response materials in a low displacement curves, let's say, and there's just a slight change or variation between these two curves. But in terms of the strain sensing capability, you would be able to achieve. So maintaining the design limit loads in a structure, which is a high performance structure, and people are very, very concerned about changing that. So you would be able to achieve a sensing capability easily. And you haven't added really anything to the weight or the thickness of the material if you use that. That's where actually we're doing research that come up with a 3D double curvature demonstrator level, and we're focusing on the ring box demonstrator now to make it fully from this smart structure and making the wind tunnel at the University of London. So of course, yeah, we need loads of wishes and lucks for to carry out this research, but that's where we would like actually to identify some other uncertainties associated with this scale-up. And I would like to draw your attention towards a paper we published in 2017 in a SERP Annals journal that you would be able to identify that quickly. That we covered this scale-up issue with identification of the effect of process parameters on the mechanical performance, and that's also called a novel composite assembly correlation technique. That I would like you, if you actually study our research, have a look at that as well. Thanks very much for your time. Sorry about running out of time. I'm happy to answer any questions.
Who is having a question? I'm asking him to on stage. Gustavo, you can ask.
Hi, thank you for let me ask the question. Representation. I have a quick question. What do you expect is going to be the degradation over time of the response?
Yeah, we haven't actually investigated the aging or creeping of the creeping response, if you're referring to that on the structure, to be honest with you. But we published in 2016 a paper on the journal Polymer on the effect of, and actually we addressed some effect of this aging on the specimen. On the journal Polymers, you would be able to identify, I cannot find, yes, it's what's called effective morphological effect, something like that.
Yeah. All right. So do you expect that? But can you guarantee a minimum of years now? That, I mean, in a year you wouldn't expect that. And I'm not saying only because of stress, but what about light or any environmental effect?
Well, to be honest, from our research now, we cannot guarantee that. That will be the answer, unless we do a precise experimentation that we did with the hygrothermal analysis on adhesive bonds, for example. But it is a possibility that we are using aerospace grade specimens and materials. There's a possibility that we're actually, in terms of satisfying the needs for continued airworthiness for aerospace, let's say, that involves such aging, hygrothermal, or creep effect, we might be on the safe side of the application, let's say.
Okay. Thank you.
You're welcome.
In the Q&A section, can you take a look at that question?
Yeah, I'm just trying to. So if you consider if you consider the effect of temperature, how do we differentiate fatigue-generated cracks from creep ones? Well, you would be able to identify the use of thermomechanical fatigue testing, for example, as well as carrying out at the side of it as having a reference base. You would be able to actually carry out, let's say, a creep specimen when you load the specimen under constant load, not displacement, and let it creep at the different temperatures. For example, for our temperature, we try to avoid exceeding the glass temperature of the epoxy resin. For a structural scale, that would be nearly 100 degrees. And that's okay for aerospace, because the varying temperature loads that they might have during service is from -35 to 85 degrees, the worst case scenario, let's say. That's a possibility that you would be on the if you mean the laboratory scale experimentation, you would be able to carry out different sets of experiment and then identify the differentiate the fatigue generated cracks from the effect of temperature. That's from the top of my head. And said, since that's the first question, I hope I answered. We're currently adding in a non-distinctive pattern CNTs since we're currently adding in a non-distinctive pattern CMTs, will adding them in a unidirection make a difference to mechanical properties? Obviously, yes, it does. If you're talking about highly oriented carbon nanotubes produced with these very well controlled CVD, for example, yes, of course you will. Just imagine in a carbon fiber composite as well. People come up with different orientations across the composite laminates, right? And that's why they need a specific. They need to satisfy a specific direction in terms of mechanical properties. So wherever you line down these carbon fibers or carbon nanotubes for our case, you would strengthen the material towards that direction. But be careful, we cannot compare the carbon nanotubes orientation with the fiber orientation. We can only compare that with the chop fabric ones that you have short carbon fiber dispersion, let's say, or chop fabric they call it. But it is, yes, of course, yes, that will make a difference as well. So it depends really what is the application that you're looking for. If you're looking for just increasing the mechanical properties across the thickness, you can just look at aligning your carbon nanotube or embedding highly aligned carbon nanotubes as a thickness or rails between two different composite plies, and then you will achieve through the thickness properties. I hope I have answered this question well.
Okay. So we thank you, Herman, again.
You're welcome.
So let's
Thank
move
you, everyone. Thanks.
to our last paper. Is about empirical modeling of frictional noise and two-point contact using bond stick. I think this paper will be presented again by Hans Shams.
Yes.
Right? Okay. You can start.
Okay. Good afternoon now, everyone. I guess 12 has passed, so I should welcome everyone as good afternoon. I'm basically the second author on this paper, so this is not my primary work, but I'm presenting on behalf of the main author. So this work is about the empirical modeling of frictional noise and two-point contact using ball and disc tribometer. Our supervisor is again Dr. Muhammad Ali Khan, who is looking into this work. So the authors and affiliation goes something like this. So the first author in this paper is basically Kanza Basit. She's a student at National University of Science and Technology, Pakistan, and I'm the second author in this paper. So this work was jointly supported by Through Life Engineering Services Institute and Engineering Sciences Department at NUST. Before moving on with the actual work, which is we're first going to understand what we are talking about, which is how does the wear actually is occurring in this particular experiment, and what exactly is the novelty of this particular work. So we'll first define what is sliding wear. If you look at this flowchart on your right over here, so friction and wear of sliding pairs can occur through microgeometrical pairing properties. It has an effect on because of the metallurgical properties, tribochemical properties, loading and macrogeometrical properties, environmental properties. So they all basically contribute towards the sliding wear. The surface damage that occurs during the sliding is by deep surface grooving due to penetration of asperities or foreign particles. That is under investigation here, but we're basically only looking at the macro level friction and wear. We're not really considering the asperitical or micro level work over here. So we would be just talking about the penetration depth for that matter and how it changed over time. The surfaces may be metallic or non-metallic, or obviously that does not really make a difference because as long as you choose the right ball and surface combination, you'll still be able to end up with good wear combinations. So what exactly is sliding wear? These show some mechanisms over here on A, B, C, D. So the first one is basically adhesive junctions, where you might have some stickiness or, basically localized welding that is taking place at these joints, which are responsible for the removal of the material from the above and or bottom. It depends on which one is more, it has more strength actually at the end of the day to keep their elements intact. And it can also happen because of plastic deformation as shown in the B. It can happen because of the cracking in brittle solid. So you can have the material wearing off. If you say have a ductile solid on top and a brittle solid on the bottom. And because of tribochemical reaction, you can also have these small asperities leaving the surface. So the sliding wear can happen in all forms. What we're basically investigating is, while the sliding wear is taking place, you will obviously hear some sound. So we're basically trying to model that sound and wear together. But the novelty at the end of the day is that we are using multiple contacts, which is something still very much new to the literature, as opposed to single point contacts, which is well established throughout the literature. So what exactly is frictional noise? Frictional noise is due to contact of materials. We identified two categories of this frictional noise. One is the rubbing noise, which is always there, and one is the squeal noise, which is that high-pitched sound we get to hear whenever a penetration depth is increased drastically during the sliding wear. So when the coefficient of friction between ball pin and the disc is small, the vibrating energy is small, and therefore the frictional noise or is rubbing noise, which is a low level. And exactly what I explained right now, when the coefficient of friction increases as a result of increasing contact region, ball pin gets worn and the rod holding the ball pin vibrates in lateral direction, which increases the vibration energy and leads to higher frictional noise, which is also known as a squeal noise. So if you look at the amplitude of these two sound pressures, rubbing noise has like 65 decibels of sound pressure, sorry. And the squeal noise goes all the way to 95 decibels and it keeps on increasing. So these transient waves that you see on top of here are actually squeal, and these small, that repetitive ones that go underneath are usually rubbing noises. So this is a common trend that you see in any sound signal that is generated while a sliding wear is taking place. So when what is the relationship between wear and frictional noise? So when two materials are in contact, wear is generated. Consequently, frictional noise is also generated. We can compare the two as the same, the acoustic emission and frictional noise. So some may actually have an argument against this, but once you change the frictional noise signal into an FFT, you get the same as the acoustic emission signal. So they are very much comparable as seen in the literature. Tool wear monitoring in cutting, milling, and sliding finishing are some of the ways in which you can see this effect more predominantly. The relationship between different types of wear and frictional noise vary with properties being analyzed and the conditions being evaluated. So if you change load, speed, and lubrication, you're going to end up with different wear and frictional noise combinations. So again, as mentioned previously, you always have a rubbing noise signal going on. So this continuous acoustic emission signal that is over here, and you see these transient spikes over here. So these transient spikes are usually because of the squeal noises, and continuous AE signals are usually because of the rubbing noise that is always generated. A similar plot can be seen over here, where you see this time variance signals going on over here. So like I said, frictional noise can easily be converted into an acoustic emission signal by taking an FFT. So you can even identify different materials over here based on the specific frequency noise, because this is also a technique that is used in material forensics. So by identifying specific materials that are in contact, we can use it for material forensics to identify which two materials are actually undergoing wear right now. And a similar plot is seen over here, that when the load cell actually comes in contact, you see a high transient signal over here, and whereas it progressively decreases over time. So this is what our equipment actually looks like. We have obviously a much better equipment over here in Cranfield. So this is the basic schematic. We have a disc that is rotating. You have a cantilever arm, which is housing the two ball equipment over here. So these two balls are in contact with the disc and continuously rubbing. And you have this angular velocity going on. The weight is applied in the normal direction. And the friction force is obviously generated laterally. So you have the simple mu, which is the simple frictional coefficient equation taking place. So that is how the CUF value is calculated for each particular interval. This is another way to actually show how the two signals are basically measured. So you have an acoustic analyzer, which is generating that plot directly, or you can use a microphone setup, which we have used. And you can take these data to the computer and generate an FFT on your own. But right now, for this particular investigation, we just modeled the sound signal on its own and did not really go with the acoustic emission transformation. So we're just going to be talking about the sound signal in its purest form. And we're going to actually evaluate how, when you move from a single point contact to multiple point contact, how does the behavior of the sound change and how you can actually compare it with the single point contact. So why consider multiple contact? Because extensive research is already performed on single pin, whereas effect of multiple pins is insufficient. A machine part is in contact with more than one component at the same time, and we wanted to replicate the actual machine environment. Every component may have different forces acting onto it. It is essential to analyze the effect of normal as well as external forces so that you can quantify wear in correlation with frictional noise. So the problem statement was when a machine runs, one machine component is contact with more parts, as explained earlier. It is important to affect each contact. Studies pertaining to interaction between two components have been conducted, and pressing research is to research about multiple contact. And it's a useful tool for fault detection in machine component. So right now we're using same material combination, but subsequent research that we are currently doing, we are actually using multiple material combinations. We have multiple disc and ball combinations. So the research objectives for this particular work was that we designed a 2-ball holder for an already available tribometer in B30 lab in Canfield, which is TRB cube, to test the efficacy of 2 balls sliding on a disc, to observe progression of wear and frictional noise in this particular scenario. And I wanted to identify specific regions for wear and frictional noise by trend analysis. So we took 2 stainless steel ball bearings of 6 mm diameter. This is like the experimental methodology well explained in the paper itself. So we are just going to explain this figure. So basically this 2-ball holder is placed eccentrically on the disc. So you can generate 2 different wear tracks. Obviously this is kind of explained more in the picture in the next slide. But if you can visualize this you are basically, you can control this distance as per your will. But if you move this ball holder in the center, you're going to have a single wear track where 2 balls are basically causing the same wear. So this is what the experimental setup actually looks like. This is the 2-ball holder. You have a microphone here, you have a 20 Newton load being applied, and you have a mild steel disc. The 2 stainless steel balls are here and here. So you're generating basically 2 wear tracks. These are the experiments that we performed. In first, we basically took the stainless steel ball on its own. The second one, we took the stainless steel ball only in ball B and nothing in ball A. And in the final one, we basically took the balls in both the holder positions, and then we investigated the wear. So basically we took an average of these 2 values and compared it with this one to specify how the wear actually translates when you move from single point contact to multiple point contact. So these are the results. As you can see, individual results of pin A experiment 1 and pin B experiment 2 are averaged out to form pin AB and AB averaged. So this particular orange line is basically when you take the average of experiment 1 and experiment 2 and you plot it on this particular graph, which is penetration depth against time. And pin AB are combined results which follow a very similar trend to the one shown before. They're in good correlation. If you even see the values, this is like only a 20 micron difference more or less at this point. Or okay, more than that, a little slightly more than that. And if you look at the sound pressure, again, this is in good correlation, except for this spike in running in region, which can be averaged out as well at this point. Again, this is not really a significant sound pressure difference. The overall trend shows a very strong correlation between the 2 graphs on its own. The 3 regions that are initial transition and running in are identified based on the change in the graph shape. So these are not really a specific quantity that you can pick it out that I'm going to fix this on this particular time, but based on the graph changes, this is being plotted on this particular experiment. So the initial region is from the 0 to 90 seconds. Both the wear and sound are progressing rapidly in this region. In the transition region, the progression becomes more gradual. And in this region, both the wear and sound starts linearizing, from which it can be concluded the wear and sound stabilizing over during this time. So that is how these 3 regions are identified. So the initial region is when the progress is more rapid, and when it goes on to become more gradual, you define that region as a transition, and the running in is when the sound and wear stabilize over time. So in conclusion, we validated that 2 balls sliding on a disc combined and 2 balls sliding on a disc average follow similar trend. So this is our hypothesis right now because we haven't tested it as such, but say if we increase this contact to 3 balls or 4 balls, we should be able to follow similar trend, and that is something we can validate in the next part of the research. And it shows a strong correlation between penetration depth and sound pressure. This shows that our methodology is in line for subsequent experiment for using multiple ball disc material combinations as well. In the future work, we conducted similar experiment, which we're doing right now for multiple ball disc material combinations, and we are identifying distinct material combinations based on frictional noise. So if you can basically model the sound pressure, you might be able to eventually, by taking an FFT and everything, you'll be able to identify the material forensics as well, as to what two materials are in contact right now. That is obviously the work of the lead author, so I'm not really abreast on that information. I might be able to share that in the later part of the work. So regarding the questions, you are more than welcome to ask me questions regarding the presentation. I'll try to answer them to the best of my knowledge. But if you have any specific questions, please feel free to email me. I can communicate with the lead author and let you know about the answers to those.
Is there any questions from the audience? So no questions? Okay, we thank the Hams again. So
Thank you.
I think now we finish all of the paper presentation. So I think we can conclude our session too. So, Archie, do you have something to say?
Yes, you can carry on, then I will say at the end.
Okay. Yeah, if you have something to say,
Okay.
go ahead.
No, that's a closing announcement of this session. So if you have any questions or comments, you can say, then I'll just conclude this session at the end.
Okay, so thank you all of you to attending our session 2. I think we have 5 good presentations. Hope all of you can enjoy, and I hope to see all of you maybe next year, so we can meet in person. So thank you again.
All right. Thank you, everyone. Thank Rukyang for chairing this session. Thanks, everyone, for the outstanding talks. So we'll be closing this session in few minutes. So after this closing of this session, you will be sent back to the main auditorium. And then again, we will be reconvene at 1 o'clock. We have the lunch break in between. So at 1 o'clock, there will be keynote lectures at main auditorium. So you are requested to join in that session. Till that time of 3:45, I believe, we do not 3:45. We do not have any session at room 2. So we will reconvene at room 2 at 3:45 with again the next set of lectures. Thank you, everyone, for joining us. I'm switching off the session right now. Okay. I see some chat messages. Okay. All right. Thank you, everyone. Bye-bye.
Bye.